So I'm going to review today and answer any questions you might have. The final exam is usual 2-hour thing. Let's see, it's Thursday, May 8th. Um, 8 to 10 a.m. in Stanley Coulter, just kind of next door, 239. So I'm going to review today and Wednesday. You can find practice problems for the final exam and an old final. Find on the home page. And I need to cancel class on Friday. Not going to be here, so no class on Friday. I assume by then I'll have reviewed enough, but if you have more questions, you can always put them on Piazza, and I'll be having office hours next week that I'll announce. So, any questions about anything? Yeah.
So the exam's 40% of the final grade?
Let's see.
50? Yeah.
100 for the midterm, 100 for homework, and 200 for the final.
Yeah.
That's how it works.
And then how many questions would that be?
I'm thinking between 5 and 8, so still thinking about it. Other questions about anything? Well, let's see, I want to review some things. I figure this is a good way to review the Liouville's theorem, which is an important thing from early in the class. And it's the main tool in demonstrating a famous thing called the Casorati-Weierstrass theorem. Fancy name for kind of an easy thing. It's a way to this is a way to review Liouville's theorem and the kind of linear fractional transformation tools that we have at our disposal now. So let's see, this theorem says if an entire function misses an open set, it has to be constant. I'll tell you what I mean by in misses. Let's see, an entire function that misses an open set must be constant. It's kind of like I told you about the little Picard theorem. Well, this is even a littler Picard theorem. And it's older than the Picard theorem. Well, the demonstration is fairly straightforward. So missing an open set means that it misses if it misses an open set, then of course it would miss a disk. So let's see. Let's suppose we have an entire so entire functions means that f is analytic on the whole complex plane. That's what entire means. So I've got an analytic function on the whole complex plane. Missing a compact, let's see, if f, you think of f, the image of the whole complex plane. If that misses an open set, let's say an open set O, then it also misses a disk, any disk that would be in that set. then there would exist a little disk of radius epsilon about, how about W naught, such that the disk of radius epsilon about W naught intersect the image of the whole complex plane under F is empty. That's what it means to miss, well, that's equivalent to missing an open set if it misses a disk. Okay, so let's think about why Liouville's theorem might be relevant here. So here's the picture of F. F is mapping the whole complex plane. So my usual picture of shaded region is the whole complex plane. It would map that to a blob. And the blob would be missing a disk, that little disk of radius epsilon. Okay, so we'd have here a little disk of radius epsilon about W naught. That's W naught. And we think about how we might turn that inside out. And that's the key to what we've had linear fractional transformations that map disks to disks, and they can turn it inside out, or they can sort of leave it the same. So the big idea here is to use a linear fractional transformation. I guess it's easy to think about these in steps. I would take, let's see, first I would map it to the origin. So let's see, that would be Z minus W naught. That would map that picture to the origin. So then I'd have my little red disk would get mapped to 0, epsilon, and the F would map to the outside. Then I'm thinking I might rather have the unit disk. And so let's see, the unit disk, I could map Z over epsilon. Would map that red circle to the unit disk. And then it's still mapping to the outside of this. And now the big idea is I know how to turn the unit circle inside out. 1 over Z does that very easily. So if now I take the inversion, 1 over Z would turn the unit circle inside out, and it would map the outside to the inside. And so that blob on the outside now would get mapped to the inside. By the way, think about what would I possibly hit 0, and the answer, of course, is no, because 1 over Z would map the point at infinity to 0. So 0 actually doesn't get hit. And now you think about this composition, it's a bounded entire function. So the aha moment is, let's see, what is that? If I do all the composition, I would get epsilon over F of Z minus W naught. I believe that's what it would turn out to be when I do the composition, is a bounded entire function. And so, therefore, it's constant. Let's see. That x there means that 0 never gets hit. So it's a constant, and it's a constant that's not 0. So it's bounded entire function, and it's never 0. So it's a non-zero constant. Liouville's implies that that function right there is a non-zero constant. So epsilon over F of Z minus W naught equals C, and that's unequal to 0. And you solve now for F of Z, and you get you get that f is constant too. Solve for f. See, f is equal to constant. And that's what we want to see. Questions about that? Liouville's theorem was kind of an important thing, especially in the fundamental theorem of algebra proof and various other places in the course. Yeah.
So, knowing the how those linear transformations like affect the graph, is that going to be like important to know and stuff?
That's one of the practice problems. There's a question about that. Let's think. Let me look at the practice problem here. Practice problem. Where is it? Doggone. No, it's. Let's see. Where did that go? An old exam had a question like that, I think. Yeah. The old exam number 7. Let's see, I gave you, let's just do one of them maybe. T1 of z is z over 1 minus z. So the question is, what could be asked about linear fractional transformations? And the question here asks, what is the image of the unit disk? So the question is, what does it do on the unit disk? Well, it's a linear fractional transformation, and so we know it maps lines and circles to lines and circles. So let's see, the unit disk would be determined by 3 points. Let's see, 0 would be an easy thing to calculate. Let's call A is 0. Oh, B is interesting. 1 is interesting because 1 gets mapped to the point at infinity. And so that's something. Minus 1 might be interesting to look at. And then probably I need one more point to figure out where the circle goes. Circle is determined by 3 points. So maybe an easy one would be I here. So let's call A, B, C, D. Okay, so T1 of 0, of course, is, what is it? 0. And T1 of B is the point at it. So 0 is A prime. T1 of 1 is the point at infinity, so that's B prime. T1 of minus 1 is what? Yeah, minus 1/2. That would be C prime. And now I need T1 of I. So T1 of I would be I over 1 minus I, which I would multiply top and bottom by 1 plus I, the conjugate of the denominator. That would give me 2 on the bottom and minus 1 plus I here. And that would be D prime. Okay, so I've got B prime, C prime, D prime. That's 3 points. And T1 of B. Oh, I don't need 3 points, do I? Why don't I need 3 points? It maps. I know it maps to a line because B gets blown out to infinity. And so if that were a circle, of course, it wouldn't get anywhere near infinity. So I know now that circle, unit circle, maps to a line. And so 2 points determine a line. Okay, so I don't actually need this. I don't need this third. Oh, I do. Yeah, there's 2 other points. I need 2. So Sorry, I do need that. I need C and D. But those 2 points are going to determine a line. So let's see, I've got minus 1/2. That's right here. So that would be minus 1/2 is C prime. Where's D? D is minus 1/2 plus I. Interesting. Minus 1/2 plus I is D prime. And now I know that that green circle gets mapped to this green line, determined by those 2 points. And now the question is, okay, where does the inside go? And A equals 0 gets mapped to 0. Therefore, the 1-point test would tell me that this shaded region gets mapped to this side of the green line. That's the kind of questions you can answer using the basic facts about linear fractional transformations. The biggest fact is they map lines and circles to lines and circles. Questions about that one? That's a good question. Yeah.
So, is the reason that we know that 0 doesn't have to be on the line because it's not on the boundary of the circle in the original program?
Right, it's on the inside of the circle, well inside. And so, yeah, that circle gets mapped to the line, but the rest of it, remember, that cuts the Riemann sphere into 2 pieces. And we know that linear fractional transformations are one-to-one onto the Riemann sphere.
So we want 3 points to define our circle and or line, and then we want at least 1 point to define.
That, or you could use the bug test. Let's see, the bug test, let me have a bug that crawls from, why don't I crawl from C to D? So then the tangent vector would be going like this, and the normal vector, crawling bug, is pointing to the inside of that disk. And so as this bug now on this side, the image bug, crawls, the normal vector points to the right, so that would be the right legs. And using conformality then, using the bug test, I would see that the shaded region goes to the left of the line. So bug test or 1-point test. 0 was such an easy thing to calculate that I chose the 1-point test in this case. Other questions? Yeah. If I were going to draw B prime, here's what I would do. I kind of like, this is the way B prime is the point at infinity, so it's kind of, I think of it as on this line. If I drew it on the Riemann sphere, that means that would be a slice of the Riemann sphere, and the point at infinity would correspond to the North Pole. And that green thing on the Riemann sphere would go through the North Pole. That's why I like to think of it, yeah.
So, kind of like geometrically speaking, is it, based on the Riemann sphere, is it all circles, but because it's a point at infinity, it makes a line?
It looks, well, in the plane it's a line, but on this Riemann sphere, it would be a line of longitude going through the North Pole. So, yeah, that's why it's easier to say on this Riemann sphere, linear fractional transformations map slices to slices. Other questions? That's a good problem. And fair game on an exam, because it's not too hard to do using the facts. I wanted to mention a key fact, and this demonstrates. Here's a good fact, or let's call it a tool, an important tool. We had this, well, let's see, here, remember the residue at at a point A of f over g. There's a simple formula for that. So rather, if it's a polynomial, and rather than factor it and do all kinds of nasty arithmetic with complex numbers, the residue of f over g is simple to calculate when the thing in the denominator has a simple zero. When f, g are analytic near A, and A is a simple zero, meaning of G. And what that means is that G of A is equal to 0, but G prime of A is not 0. Okay, that simplifies a lot of calculations of residues, especially when the bottom is like a polynomial of degree 5 or something. Those can be difficult to factor. That's kind of a knee-jerk thing to do. But so the question now is, what if G has a double zero? That would mean that G of A equals 0, G prime of A is equal to 0, but G double prime is not 0. That's the meaning of a double zero. Well, there's a formula that's in all the books which I detest. So let's see. I'm thinking out loud now. F of z over g of z would have a double pole. Of order 2 at A. Okay. And so that means that the Laurent expansion would look like b over z minus a squared plus, or let's call it b2, b1 over z minus a, and then plus power series, regular power series. And so the residue is right there. And so the book has this, let's see, so what does the book do? It says, okay, let's multiply through by z minus a squared. Our book and all the books would say, okay, multiply by z minus a squared, and you get a b2, and then a b1 times z minus a, plus etc. And we want the b1. And this would be analytic, because it's equal to a power series. So this is analytic here. So of course it has derivatives and limits, etc. And so, what does the book say? What does it say to do? The limit? Yes. I hate this formula. Let's see, so what does it say? That's the first coefficient. I mean, that's the Taylor coefficient of that analytic function. And so it is 1 over 1 factorial times, we know this thing is analytic, so it's going to have a limit as z tends to a of the first derivative, d by dz. I'll put 1 here because in place of 1, there might be an n. If this was a higher order pole. So this is d by dz of this crazy thing. Z minus a to the 1 plus 1 f of x. If this were a higher order thing, I'd have to put higher order things here, not just 1. That's a ridiculous formula because it's not that hard. It's just messing around with power series. So I don't like people to memorize this formula, and I don't like them to use it because it leads to calculations which are harder and which are more like doing L'Hopital's rule than anything else. So here's a better way to do it. Okay, so if this was a polynomial, if g was a polynomial, I'd like to factor out the z minus a squared from it. And then I could play around with power series. So I will have g of z. Let's see, its Taylor series would start with a naught plus a1 z minus a. Those both would be 0. Plus a2 z minus a squared plus blah, blah, blah. This one is equal to g of a, and that's 0. This one's equal to g prime of a over 1 factorial. That's 0. And this one, a2, is equal to g double prime of a over 2 factorial. And so this g of z, now, I can factor out the z minus a squared like we always do with power series. If it has a 0 of order 2, I factor out that, and I'm left with, I'll call it capital G, where I could calculate all the derivatives of capital G I wanted. So let's see, g of z equals a2 is the first term, plus a3 times z minus 1, a, plus blah, blah, blah. Let's see, I know what a2 is. A3, if I cared, I probably will care. Will I care? I'll see if I care later. A3 is equal to g triple prime of a over 3 factorial. Okay, and now here's the best way to do this problem. My f of z over g of z now, little g of z, is f of z stays there, and then I'm going to pull the z minus a squared out in front. So I get 1 over z minus a squared times f of z over capital G of z. And that's a nice analytic function. And it's non-vanishing. So I would call this an h of z. And let's see, it would be a naught plus a1 times z minus a plus, etc. And that's analytic, because the g is non-vanishing. So we notice that g of a is equal to a2, and that was g double prime of a over 2 factorial. And that's unequal to 0. So this thing is analytic near a. And so now when I look at that and distribute the 1 over z minus a squared through, I'd get a naught over z minus a squared. This is the actual Laurent expansion, by the way. If I asked you to get the Laurent expansion, this is what you would do. And this a1, and we see, aha, that's the residue. And the rest would be just regular old power series. And so the A1 is the residue at A. That's what I want. And notice what that is. That's the A1 in the power series expansion for capital H. So I see that A1, the residue at A of f over little g, in this case is A1, and that's equal to the first order Taylor term in the expansion for h. So that would be h prime of a over 1 factorial. And h is the quotient. So the quotient rule would tell me that that's equal to f prime of a times g of a minus g prime of a times f of a over g of a squared. And let's see, what's g prime of a? G prime of a is a3. I should have written that right here. I was afraid I would need it, and I do. G prime of a from the Taylor series is a3, or I should say, yeah, a3 over 1 factorial. What? No. G prime of a over 1 factorial is equal to a3. And that's equal to g prime. Yeah, well. And a3 I know is g triple prime of a. What? It's over there in the right-hand corner. That's where I was writing. I'm sorry. This is where I was writing. Oops. Sorry. Yeah, that you just read off from the power series, what those various derivatives of capital G are. And you go back to where those little a's came from the power series for G. Anyway, if you keep track of everything, then you can calculate those things, and you see that the residue is, let's see, f prime of a is a thing. G prime of a, G of a is the a2 term. So that would be g double prime of a over 2 factorial. And the g prime of a is g triple prime over 3 factorial at a times f of a divided by g of a was g double prime over 2 factorial. And we square that. And you get a formula that you could clean up and write in. There's no point in memorizing those formulas because you just do it every time. So let's see an example where you would do this. Rather than memorize this formula or any formulas, let's say I had something like, how about e to the 2z over 1 minus cosine z. That would be e to the 2z, that's over, cosine of z is 1 minus z squared over 2 factorial plus z to the 4th over 4 factorial, etc. So this would start with a z squared term. Z squared over 2 factorial minus z to the 4th over 4 factorial plus blah, blah, blah. And I do this, I'd factor out the 1 over z squared and get 1 over z squared times something that's analytic. And it would start with 1 over 2 minus z to the 4th over 4 factorial. What? Oh, you're right. When I pull out the z squared, this would be a z squared term. Okay. And this I would expand in a regular power series and get a naught plus a1z plus blah, blah, blah. And I would see that this is a naught over z squared plus a1 over z plus power series. And there's the residue right there. And that's this is could be, I would call this thing an h of z. And it would be easy to calculate that a1 term in terms of so the residue at 0 would be equal to a1, and that would be equal to h prime of 0 divided by 1 factorial. And that's a pretty easy thing to calculate. In fact, the fact that there's a missing term in the power series in the denominator that makes the calculation easier, because you don't have to worry about that capital G prime term. It's 0. And so it's not hard that way. And you don't have to memorize the formula, and you don't have to take limits and think about L'Hopital's rule kind of thing. More questions about anything? Yeah.
Just a quick question. Speaking of like memorizing formulas, are we? Do we have a?
Oh yeah, you're allowed to have a crib sheet. That's the instructions are on the home page. I should maybe put this at the top. Let me go back to the top and write 2 sheets of regular sized paper. Handwritten only on both sides. That's a lot. That's more than you need. But if you want to just use your crib sheet from the midterm and add another one to it, that would be one thing to do. Yeah.
By sheet, you mean like one two-faced sheet of paper?
A regular size sheet, the kind of computer paper, printer paper.
4 pages total.
4 pages total, right. Yeah, so you can have a crib sheet like that. That should, anything you're having a hard time remembering, you can put there. If you want to use that formula, well, it's a correct formula that I hate. You can write it on your crib sheet, but it always makes me mad. Because that's not the way I ever do it. Other questions? Yeah.
Do you think on the exam we're going to get questions like that if we use the formula we would have to do like the third derivative or anything like that?
Oh, the worst thing that could happen is a double zero. Well, you did see a triple zero, right? In one of the homework problems. It wasn't hard because if it was a triple zero, let's see, for example, let's say you have e to the z over z squared plus 4 cubed. And let's say, then you can factor that denominator. Let's say we're at z equals 2i. We'd have z over z minus 2i times z plus 2i. Quantity squared. And so if I was cubed rather. So if I was trying to figure out the residue at 2i, I would pull out the z minus 2i cubed, and then I'd be left with something that's nice and analytic, not terribly hard to mess around with. Cubed. And so if I wanted the residue of this one, I would call this the h, which is not terribly hard to deal with, and I'd write it as a power series about 2i. And when I write this out now, I'd get another term that this one's going to be, I don't care about this one, but the one I do care about is the a2 term, and that's going to involve 2 derivatives of h. And the rest is going to be regular power series. And so that a2 term, the residue at 2i, is going to be the a2 term, and that's h double prime at 2I divided by 2 factorial. A very common mistake is to not have the 2 factorial there, especially if you compute it with that limit. I don't even want to think about how you would compute it with the limit, but I mean, you usually get a correct answer if you do that, but it's more there's more traps because it's kind of like doing L'Hopital's rule twice. Other questions? See, there was an important residue calculation I wanted to review. It was a homework problem, and I wanted you to think about it. That doesn't look very good. So let's see, I'm going to have a... Here's 0. Here's r. I want to calculate the integral from 0 to infinity of 1 over x squared, x cubed plus 1. So let's see, so we're going to take f of z to be z, that thing in the integral. F of z would be 1 over z cubed plus 1. The complex numbers whose cube is equal to minus 1 are e to the I pi over 3. And minus 1 is over here. And there's another one over here, e to the minus I pi over 3. Or 2 pi over 3, however you like to think about it. Okay. And this point right here would be, I'm going to take this angle to be 2 pi over 3. And it turns out, let's see, if I call this part of the integral c sub r, I'll call this part of the integral line, and I'll call this one L1, this one L2. It's easy to show that the integral around the circular part goes to 0. The integral around L1 is the one you want, and so you got to think about what is the integral along L2. And so this point right here would be r e to the I 2 pi over 3. That can't be right. What am I saying? Yeah, this is a 5 pi over. Yeah. Okay, so you're going to use the residue theorem. And this is an example where you've got a simple 0 in the denominator. And so you can just write it as 1 over the derivative of that bottom thing at the point e to the I pi over 3. So the problem is to figure out what the integral along L2 is and how it relates to the integral you want, which is the integral along L1. That would be the integral from 0 to r of the thing you want. You just let r go to infinity. So here's what I like to do. L2 is going the wrong way. I like to parameterize by a t that starts at 0 and goes to r. So I like to parameterize. I like t equals 0 dot dot to r. In my parameterizations. And I can get that if I parameterize minus L2. Then, let's see, that starts at 0 and goes out to r e to the I 2 pi over 3. So an easy way to parameterize that would be to have t times e to the I 2 pi over 3. Okay, and when t is 0, that's at the origin. And as t slides out to capital R, that takes me out to that left-hand corner. Okay, and now what I really care about is the integral along L2 of f of z dz. But that would be minus the integral along minus L2 of f of z dz. And that would be minus the integral as t goes from 0 to r of 1 over, here's the reason we chose that angle. So this is t times e to the I 2 pi over 3 cubed plus 1. Oh, and the z prime of t would be e to the I 2 pi over 3 dt. So this right here is z prime of t dt. Okay, and the great thing about e to the I 2 pi over 3 cubed is that it's e to the I 2 pi, which is 1. So, in fact, the great news, and the reason this angle was chosen, is that this comes out to be t cubed. And so sure enough, this is related to the integral we care about. This is, I can pull out that e to the I 2 pi over 3. I get a minus of it, and then I get the integral I want, which is 1 over t cubed plus 1 dt. And I want that. And so great news, it's not going to cancel the integral L1 when I add it all up because of that factor in front. It's going to give me something usable. And in fact, this is how you choose that angle. So whoever thought about this, if I had my L2, if I had it be, if minus L2 was t e to the I alpha, for some other alpha, when I did this, I would choose the alpha so that its cube is equal to 1. So that's why this was a brilliant thing to do. We would need e to the I alpha cubed to be equal to 1 to make this work. So I could have invented that and chosen it by being, motivated by this thing rather than pulling it out of the hat. Anyway, that was an important homework problem, and I let you think about it. I was expecting people to ask for hints on Piazza, but they didn't. But it's important to know how to do that one. Other questions about anything? Got a minute left, roughly. There's classic problems. What's the radius of convergence of, I'm going to mess it up, log Here's one I won't mess up. Sine of z over z about z equals pi. Anybody say what it is just by looking? Yeah. That's your knee-jerk thing. You think, oh, that looks like it might have a singularity at z equals 0. But in fact, that's a classic case of a removable singularity at z equals 0. And so that thing is actually analytic. If I give it the right value at z equals 0, I can make it an entire function. If I give it value 1 at 0, it becomes entire. And therefore, of course, if it's entire, then the thing is analytic on the whole complex plane, and the radius of convergence is infinite. Give it the value, it's entire, r is infinity. Our radius of convergence is